computer. Okay. All right. So we so what I want to do today is just kind of review some basic concepts of geometry and coordinates and things. We will definitely have, more than just simple points. But we will pretty much limit ourselves in this semester to lines, rings, or maybe a half, portion of a ring. Okay, so circles. Those would be kind of shapes we have, or discs, or planes, like an infinite sheet, or spheres or cylinders. So we will have some non-trivial shapes, but they're not going to be too crazy. We're basically going to limit ourselves to all of the shapes of high symmetry. Okay. So I kind of want to go through the coordinates and things that are relevant for those. We're not going to do something complicated like, a picnic table covered with charge. I mean, that would just be kind of beyond our pay grade in terms of the calculus involved. So, okay. So let's kind of go back to the beginning here with dimensionality. For those of you who were in dynamics earlier, this came up a little bit, but so we will have various shapes that we'll break them down according to one-dimensional geometry, two-dimensional geometry, and three-dimensional geometry. The real way that I would say that you tell the difference is how many numbers do you have to specify to describe it. So if it, in the one-dimensional case, you can describe where you are with one number, okay? Namely the length along the curve. So in the case of something that's a straight line segment, it's kind of obvious. You just, put little tick marks, but really that's actually what you would do in any case. So if I do this, hopefully I got it. Okay. So you would just imagine little tick marks, 1, 2, 3, 4, 5, 6, 7. And by specifying how many tick marks, that would tell you where you are along that curve. And here, again, you specify one number, the number of tick marks. And that would tell you where you are along this curve. So by specifying one number, you can know where you are on the curve. Therefore, it's one-dimensional. Okay? If you can describe it by specifying one number, it's one-dimensional. That doesn't mean it's straight. Okay, so for example, if I had a half hoop of wire, that's a one-dimensional curve. Right? It's just a wire that's bent like that. Oh, wait. Because we're so excited to be doing physics, our half hoop of wire should look like this. There we go. All right. A two-dimensional shape. What makes something two-dimensional? Well, if one-dimensional shapes can be parameterized with one number, two-dimensional shapes are kind of coordinatized or parameterized or described by two numbers. Well, we kind of know that, right? You specify, because we lay out grids of things, right? And so we'd specify so much in the X and so much in the Y. Two numbers are needed to coordinatize the two-dimensional shapes, okay? Or, as we'll talk about in a minute, you could do a radius and an angle. But again, that's two numbers. So two numbers. So if it takes two numbers to describe it, it's a two-dimensional shape. And then three-dimensional, if it takes three numbers, it's a three-dimensional shape. So you'd have, X, Y, Z, or cylindrical coordinates, or spherical coordinates. But all of those are three parameters. So you could have X, Y, Z to describe a point in here, or R, theta, and Z for cylindrical coordinates. And what about spherical coordinates? What would Stephanie say for, or I don't know, who'd you have Calc 3 with? Stephanie or Aaron?
Stephanie.
Stephanie. All right. Well, what would Stephanie use for the coordinates in spherical coordinates?
Rho phi theta.
Right. Exactly. That's what she would do. I won't do that. Rho is the symbol used for density, and specifically charge density. And so I don't want you to get confused between charge density and just the coordinate, length, or so I will, in spherical coordinates, I will use r, theta, and phi. And this r is spherical coordinate r, and this r is cylindrical coordinate r. It won't be confusing because, to be honest, you look at the shape and you see, oh, does it look like a cylinder? Use cylindrical. Does it look like a sphere? Use spherical. So you kind of interpret it as appropriate. But that's how I will do it, because I don't want you to use rho and confuse it with charge density. So, all right. When we talk about one-dimensional shapes, you should be thinking about lengths. 2D, you should be thinking about areas. 3D, you should be thinking about volumes. Okay. It doesn't make sense to talk about the length of a cube. It doesn't make sense to talk about the area of a line. Okay. So you got to get the right kind of, just when you start talking about 1D, 2D, 3D, that should already set the stage of what's even a reasonable question to ask about. Questions on that? I know it should be pretty simple. Most of you guys were in Calc 3 last semester, I think. So hopefully it's obvious.
Right. Sean, are you going to post this to
yes.
Blackboard? Okay.
I will export it as a PDF, and I'm also recording it and just going to upload it to YouTube.
Okay.
Yep. If I forget, ask me. I'm not trying to hide it. It's just I forget. So if you need it there and it's not there, tell me it and I'll just do it. All right. So let's talk about different coordinates. How do you draw coordinates on these? I guess I skipped the 1D case. Hopefully that's pretty easy. Okay. 2D coordinates. So we know about X and Y. That's easy. We also have polar coordinates. So one of them is indicated here, and then we also have R, right? The radial value. So how do we go back and forth between, so to say there's a point here. How do we go back and forth between spherical and polar coordinates? And the hint is really in this picture, if you think about it. So if I said, can you write X in polar coordinates, and can you write Y in polar coordinates? How would you do that? Trig, yeah, that's it. So I'll do that here. So what I would kind of do is, here's my point, and you just kind of drop down. Just think, see the kind of there's a triangle that sits underneath this point, and R, the radial coordinate, becomes the hypotenuse of the triangle, and theta it's the same theta, right? The angle for the point is the angle on the triangle, and so you use trigonometry to do it. So you would say that the X coordinate, all right, that's going to be R cosine theta, and the Y coordinate is going to be R sine theta. Okay. Can you guys give me a thumbs up if that looks familiar from previous course? Yeah, some people. All right. Okay, let's go the other way. So this was polar to Cartesian. How do you go from Cartesian to polar? How would you do that? Well, so you want to write something like R equals something. How could I, again, it's use the same triangle. How could you write r in terms of x and y?
Pythagorean theorem.
Pythagorean theorem, yeah. So it's always, and r is always positive. That's important. So x squared plus y squared. So note r lives, so it's greater than or equal to 0, and it's well, runs off to infinity. Okay. Right. So r lives from 0 to infinity. Can't be negative. Theta runs from 0. I guess I should write it like this. Sorry. To 2 pi. And you identify theta with 0. Theta equals 0 with theta equals 2 pi. Okay. All right. Now, very good. How could you solve for theta? How could you write theta in terms of x and y?
Inverse tangent.
Yeah, that's one way. Yeah, that'd be good. Okay, so you do tan inverse of what? That'd be tangent is opposite over adjacent, so you'd want to do of y over x. Now, you may have to add, you know how that goes. You may have to add whatever, add 90, I guess, or whatever. You may have to shift it so you get it in the right quadrant. So check quadrant, right? If you do a calculator exercise, it'll always give you something. It kind of reduces it always to the smallest domain. So you might have to add and shift it to account for other domains of definition. Okay, but yeah, you got it. Awesome. Everybody feel comfortable with that? Okay, I wasn't planning to do an example on those, but we could if you need it. All right. 3D. Well, it's the same thing. So we're just done, right? Just move on. Everybody's just as comfortable? Oh, okay. All right. Well, let's go through it. It's really the same thing, though. So here I have this picture. Make this bigger. Okay, just be careful, bud. I don't know what that was. Hope it wasn't expensive. All right. So if I zoom in here, hold on here. Alexa's telling me something. Hold on a second. I got to tell my son to start class. I'll be right there. James, you have orchestra. Zoom is awesome. If we could just do this forever, it'd be amazing. All right, so here's a kind of a picture of this. We have Cartesian coordinates, you know that, X, Y, Z. Cylindrical coordinates, those are where you're kind of imagining there's a notional cylinder and you're kind of coordinatizing the point in 3D according to where it lives on the cylinder. So those would be some sort of a radius, which is the radius of the cylinder that the point would be inscribed on. Theta is the polar angle for the cylinder that it would be inscribed on, and z would be the height above the xy axis or xy plane that the point would be inscribed on. Those are cylindrical coordinates. We're going to work through the details in a minute, but I just want you to kind of think of that. And then, so the idea, if I was going to draw this, is I pick a point in 3D and I kind of imagine that there is a cylinder that this point is inscribed on, and you're describing the point according to the radius of the cylinder. The radius of the cylinder, the angle associated with the point, and the height above the XY plane. And then you have spherical coordinates where you're inscribing the point on a sphere of a certain radius. And then there are two angles. So once you fix the radius, that you still have to specify two angles. It's morally, well, it's latitude and longitude, basically. So we'll have a polar angle, which is defined from the positive x-axis, and then we will have an azimuthal angle. All right, hold on here, guys. I have to check something at the door. Okay, so so there are two angles, latitude and longitude. The I guess longitude would be like the polar angle from the z-axis, and it'll run from 0 to 2 pi. And then latitude is like this angle. Does anybody remember the angle down from the z-axis? What name? What do we call that? What's the name of it? No. As
pi. Okay, okay.
So, and I'll say theta is the polar. Now, when Stephanie taught that, did she switch the two, phi and theta? I don't. There are some books where people do that, and I can't remember what she does. I will do it this way, where I will have theta going from the x-axis, and I will always do that. Okay, so I'll do it just like this. Theta, note then, theta, I don't know where to put it here. Theta lives from 0 to 2 pi, whereas the azimuthal angle lives from 0 to pi. So this angle only starts at the top and goes down to the bottom. So it only goes from 0 to pi. It doesn't go all the way back around. If you think about it, you can kind of do this just on your own. If you let the azimuthal angle range, if you let both of them go from 0 to 2 pi, you actually cover the sphere twice. You can hit each point twice. And so you want to somehow limit yourself to hitting each point one time. This is the way people do it. Okay. All right. Let's go through these in more detail. So here's cylindrical coordinates. We want to relate cylindrical to Cartesian, just like we did earlier in 2D for polar coordinates. So it's really pretty easy, because if you were to, imagine you were flying over the top, take a bird's eye view and just look down in the XY plane, it looks like polar coordinates, right? From the top down, this just looks like polar coordinates in the XY plane. So immediately you can say that you can use the same thing. So I would say, well, if I think about this little triangle, oh, you did that in green before. Let me try to do the same. Change colors, drop it down in green. So if you kind of look at this triangle here, there's an angle theta. The hypotenuse is r, the radius of the cylinder. X is going to be r cosine theta. Right, just coming from here. y is going to be, this part is going to be r sine theta because it's just the opposite from the angle. And in cylindrical coordinates, z is just one of the coordinates. So z equals z. Okay, is that okay? Does everybody remember doing that in Calc 3 or wherever? Hopefully you can kind of see what's happening here. It's just, you're just coming up with little triangles to help you break things down. As far as going back and forth now, then, so R is, R though, note, that's important to note. R is the radius of the cylinder, Cylindrier. I don't know. I can't spell. Sure. Radius of the cylinder, not the distance to the origin. Right? So R is the radius of the cylinder. What would be the formula for the distance to the origin? This dotted line in the picture. Well, come up with a triangle. All right? So find a triangle that you can use to figure that out. Sorry, I'm trying to get the stupid zoom controls out of the way. So look at the triangle you get. Think about this triangle right here. This hypotenuse of this triangle is the distance to the origin. And so that would use Pythagorean theorem on this triangle here. And so that would be the square root of r squared plus z squared.
Hey Dad, what's D-Day?
So just kind of remember, well, we will see some formulas like this, especially when things have sort of cylindrical shape. So, okay. You can go back and forth, just like before. Well, really, you can see that this is just, you can go back and forth from r and theta to x and y, just like you did for polar coordinates, because they're mathematically the same relationships. And then z is itself already there. So to go back and forth from cylindrical to Cartesian really is no more work than going back and forth in 2D for polar coordinates. All right. How do you guys feel with that? Do you guys feel okay with cylindrical coordinates? Usually those are the easier ones. Mason, you okay with those? Okay, yeah. All right. Cylindrical coordinates usually are easier for people to remember. Spherical are the ones that usually throw people. They have a hard time remembering the formulas. So let's go through that. Now, I apologize. This picture is the best I could find online. And so they're using row, and I don't want that. So I'm going to have to edit it here as we go through this. All right. So I'm going to call this. So what I'm going to do is I guess I'm just going to cross it out. We're not going to call. So here we are. We're going to call this R. Okay. R is the radius from the origin to the point P in spherical coordinates. So I see I can make a triangle here. I can make a triangle here with the z-axis. So that would be r cosine phi, where phi is the azimuthal angle, and r sine phi there. Okay. Let me pause there. Is everybody clear how I'm getting these two, r cosine phi and r sine phi? Right. Phi is the angle, the azimuthal angle, and combining with the spherical coordinate radius, I can make a triangle with that on the radius on the hypotenuse. I immediately see that z is this length right here. Right? It's just the height of the point P along the z-axis. So I learned that z is going to equal r cosine phi, the azimuthal angle.
R is the radius of the sphere, right?
Of the
From
sphere.
origin to the, okay.
And I'm using something different than Stephanie did. That's not right. She called that rho. That's right. She called it rho, but I don't want to do that because it will get us confused later on. Right. So you have to just kind of know, you have to understand the coordinates and you use the appropriate notation. I will be consistent though, so I won't change through the semester. Okay. R is the radius in spherical coordinates. Okay. So, right, we're shooting for a relationship so you can go back and forth between them. So we've got 1/3 of it. Right? We can, if I know R and phi, I can get Z because I can read it off of this. Now, to get X and Y, so I need to know these lengths along the X and Y axis. But what you first have to do is project down into the XY plane. So you have to project down into the XY plane and then use trig. So when you project down into the XY plane, you get, there's another triangle that you can define using theta and some hypotenuse. But the hypotenuse you get in the XY plane is not R, it's actually the perpendicular distance away from the z-axis. So that's actually going to be R sine phi. So the hypotenuse in the XY plane is R sine phi. Let me stop there because that's kind of the key to this whole thing. You see how, to get our formulas for X and Y, we're going to project down into the XY plane and then set up a triangle using theta. But to do that, we need to know the hypotenuse of that triangle. And it's going to be, it's not the, you don't get the full length R. It's just going to be kind of the part of it which is perpendicular to the Z direction, because we only want the XY, the part in the XY plane. So that's why we get R sine phi. Is that okay? Can you give me a thumbs up if it's okay? If it's not okay, I'll try to say it in a different way. Right? Some people, Gabe says it's okay. Yeah. Mason, you're kind of staring at it. Is it okay? Or are you?
Yeah, I'm just thinking it over in my head.
Okay.
Yeah.
So I'm trying to pick off. We're basically, we already figured out the Z part. We're trying to focus on the XY part. So we want the shadow of this point in the XY plane. So that means we only want the information perpendicular to the Z axis. And so that's why we pick out this. We already used cosine phi. Now we're going to use sine phi.
Okay.
All right. So now this becomes the hypotenuse. So in this image I found through the magic of Google, they've just drawn the shadow in the XY plane. So now the radius here should be R sine phi, right? That's the r, that's the hypotenuse that I have here, r sine phi, and then cross their thing out. Right? If the hypotenuse is r sine phi, remember phi, not theta. They're two angles, don't confuse them. The hypotenuse has the azimuthal angle, but we're in the xy plane. So to get the x and y part, we're going to use sines and cosines of theta, not phi. So for the x component, that's going to be the hypotenuse, r sine phi, times the cosine of theta. Whereas in the y direction, we're going to get r sine phi times the sine of theta. That gives me this portion here. So when I pull it all together, I'm going to get that x equals r sine phi times cosine of theta. Y equals r sine phi times the sine of theta. And z, we already had above, so I'll just rewrite it, is r cosine phi. How are we doing? Do you guys remember seeing these formulas in Stephanie's class or somewhere? Okay. If you wanted to go back and forth between them, well, so I'll just kind of write this in. So for example, R equals, it's the 3D version of the Pythagorean theorem. It's x squared plus y squared plus z squared. I could say, let's see if not always one way to do this. If I did if I did y divided by x, these would cancel. So I could say that theta is tan inverse of y over x. Right? Because if I do y over x, the r and sine phi parts divide away and left with tangent theta. So I get that. And if you wanted phi, how could you do phi? Well, there's not one way to do it, but one way might be to say you could do z divided by r. So I could write that as z divided by the square root of x squared plus y squared plus z squared. And then do cosine inverse on that. Okay, that's one way to do it. There are other ways, I'm sure, but okay. So you can go back and forth. We will basically, we almost, I think we probably, off the top of my head, I don't think we will use this, but rarely, let's say. Rarely, that doesn't look right. Whatever, use this one, but we will use this a lot. Okay, so we will use the radius a lot because that's associated with length and distances in 3D. So we use that a lot. We won't use this one so much. These may come up more in dynamics, to be honest, as you in that class when you're doing point particle motions, you describe in different coordinates. I don't know. Anyways. Okay, feeling okay? Hopefully you can follow where those things are coming from. All right, let's talk about vectors. So we have vectors. Today, I'm going to stick to vectors. I'm going to stick to the Cartesian basis. Okay. Later on, we'll write things in terms of spherical unit vectors associated with spherical or cylindrical coordinates. But for today, we're going to stick to Cartesian coordinate vectors. Okay, so we have a point here in 3D, and I can equivalently describe it in terms of a vector extending from the origin. So how would you do that? Can somebody call it out? How would I? Let's call it, I'd have a vector. Usually I do R for a position vector. How would I write R as a vector?
Two X hat, 3X hat, 3Y hat, and 5Z hat.
Yeah, so that's how I would do it. 2x hat plus 3y hat plus 5 z hat. Some people do 2i or I hat, either one, plus 3j hat plus 5k hat. That's fine. When you go to work in spherical coordinates, it gets a little confusing if you're used to ijk, whereas it's a little bit more intuitive when you label it according to this. What does that mean, Michael? You spoke up, so now you got an answer. What is x hat? What does that mean?
How far away it's from the origin in the X direction?
Okay, so hold on here. 2 tells me how far, though. The x hat tells me the x direction, right? So note, x hat is a unit vector. So it has length 1 pointing in positive x direction. Similarly, y hat is a unit vector pointing in positive y, z hat. All right, okay, you got it. So those are all familiar. Okay? Is that everybody's okay with that? If you have a general vector, just some random amount, you would write it as r sub x in the x direction plus r sub y in the y direction plus r sub z in the z direction. Okay. Oh, I should also remind you, Stephanie wrote vectors. She would have written this as 2, 3, 5. Am I right? Is that how she would have written it in linear algebra? Or no, sorry. Who did you take linear algebra from? That was with Aaron, right? Yeah. So she probably would have written it as 2, 3, 5. This is a really nice way to write it because it's compact, but it can be confusing because this way of writing things, you've already assumed that this is associated with x, y, and z. But what if the problem isn't nice and kind of rectangular? What if it's round, like spherical, and you're using spherical coordinates? Then it's kind of ambiguous. Does this first piece mean the radial unit vector? Does this mean the polar unit vector? Does this mean the azimuthal angle unit vector? It's ambiguous. Whereas, so when there's an ambiguity, I will write it out like this. If I really mean Cartesian coordinates, I might write it like this just because it's fast and I'm lazy. But when I want to have no ambiguity, I'll write it like this. Okay. All right. So anyways, we have these vectors. We call these unit vectors, we call these basis vectors. And these are actually orthogonal basis vectors because they're perpendicular. What is the name that we give for this number that sits out front?
A scalar?
It is a scalar. It's a number, yeah. It's not a vector. And it's a particular number that's because it's associated with the X unit vector. We call that the X component. And it is a scalar. It's just a number, like, you know, a real number, not a vector. And then we'll call and then similarly for Y and Z. So we have X components and we have basis vectors. And then the full vector is what you get when you kind of glue it all together. All right. Sometimes in a problem, you'll just know that most of it's zero, and the problem will say, oh, just focus in on the X component itself. And then they just want the number. Or maybe they really do want the whole 3D vector expression, then you got to put in the unit vectors. So don't forget those. Okay. How do we add vectors? There are two ways, right? What was the first way? How do we had a graphical way. So if I have a vector A and a vector B, how do you do A plus B?
Tip to tail?
Tip to tail, right. So you draw A. Whoa, that's terrible. How can it be that bad? All right. So that would be, so A plus B would be, you draw A, there, yes, A, and then you glue B, you glue the tail of B to the tip of A, and then the answer goes from the first tail to the last head, A plus B. Okay, that's how you do that. And when you want to do subtraction, you first multiply by a -1, which flips it, and then you just add the negative. So that's how you do that. What about in components? If I have a vector A, which is AX x hat plus AY y hat, I have another vector, which is B, which is BX x hat plus BY y hat. How do you add them in components? Component form.
Add the X's to the X's and Y's to the Y's.
Yeah. So this becomes A plus B equals AX plus BX. Wow, that's terrible. X hat plus AY plus BY y hat. So on the separate components, the scalar components, vector addition is just normal addition for the X pieces and normal addition for the Y pieces. And then you just have to remember that the X direction is different than the Y direction. Don't smush them together because the answer needs to be a vector. It's not a scalar. If you try to somehow smush them together, it's like you're forgetting that it's supposed to be a vector. Okay. Feeling okay? You guys give me a thumbs up if that's all coming back to you. Yeah, so most people. All right. Okay. What about dot products? So I have two vectors, you know, A and, I guess I have these backwards. Let's skip that for a second. How do you find the magnitude of a vector? If I have a vector A, which is, you know, AX, X hat plus AY, Y hat plus AZ, Z hat. How do you define the magnitude of that vector?
Square root of the sum of the squares.
Yeah, so it's the Pythagorean theorem. It's going to be A x squared plus a y squared plus a z squared. Okay, Pythagorean theorem. That gives you the magnitude of the vector. All right. What about if you have two vectors? How do you form the dot product of them? And there are two ways to write this, two ways to define the dot product that are equivalent.
Is this the one where you make a matrix?
No, that's the cross product.
Product.
So the dot product, first of all, maybe write that. The dot product takes two vectors and produces a scalar, a single number. So the output of this is just going to be a pure number. And the one way to do it is to say A dot B is defined to be the magnitude of A times the magnitude of B times the cosine of the angle between them, and like that. Where this, so theta is the angle between them. All right. So that's one way to define the dot product. I guess actually you can take this as the definition of the dot product. Once you use this, you can apply this to unit vectors and work at things out in component form. And it means that A dot B also equals AX BX plus AY BY plus AZ BZ. Or in linear algebra language, you could say that A dot B equals A transpose B, and you matrix multiply. Same thing. All right. If you think about two vectors, turn one of them into have a column vector and a row vector, matrix multiply, you're going to line up the X pieces, multiply them, line up the Y pieces, multiply them, line up the Z pieces, multiply them, and then add, which is exactly what this formula is. Okay. Give me a thumbs up if you remember doing this with some vectors. Not too much. Some people do. Okay. So note, if the vectors are perpendicular, what's the cosine of 90 degrees?
Zero.
0. So perpendicular vectors have give 0. Okay. Dot products know about parallel information. They don't know about perpendicular information. So if it doesn't mean the vectors are 0, it just means that the dot product somehow they don't see each other inside the dot product. Okay. Just as a comment, if I go up here and I look at my formula for this dot product, and I look at my formula for the magnitude, I see that I can write the magnitude of any vector as its self dot product and take the square root. All right, because if you take the dot product with itself, you're going to multiply the X components, square the X component, square the Y component, square the Z component, add them up, right? So if A and B are really the same, you'd have AX times AX plus AY times AY plus AZ times AZ. And that would be A dot A, and then take the square root. That's the magnitude. All right. And the magnitude tells you the size of the vector. One important thing then is we can take any vector and turn it into a unit vector. So if you take any vector, you can make it into a unit vector, and we'll call that a, if the original vector was a vector, I will call its corresponding unit vector form a hat. Hat always for me refers to a unit vector. And the way you do that is basically the vector, if it has some length, you want to rescale it so that it has length 1. So you want to divide by its magnitude. So I can, from any vector A, I can come up with a unit vector by simply taking the original vector and rescaling it by dividing by its magnitude, the scalar size. And what I'm left with is something that has length 1. Okay, so these are things that I know we did all these things in physics 1, but for some, it's been a while. And if you took Calc 3, you must have, did you guys do this stuff in Calc 3 or linear? Somewhere you did this stuff, but I know you did it with me in physics 1, but it may have been a while for a lot of you guys. I will drop the vector stuff into the YouTube playlist for this course. And then if you want to watch that, I kind of work through lots of examples. When I did those, I had explicit calculations. All right. The last thing I want to do today, what time is it? All right. The last thing I want to do, relative vectors. This is huge for this course. Okay. I can't emphasize this enough. This is huge for this course. Okay. So let's imagine I have two vectors, and I want to have a vector here. Okay, I'm going to call that RS. And I'm going to have another vector over here. I'm going to call that RO. And I'll go ahead and tell you why I'm calling it that instead of just calling it A and B. We're going to have lots of problems where we have charges that are distributed in different ways. And there's going to be an important distinction mentally when we think about things to figure out how to add up all the effects, to keep track of one charge is going to be kind of be the creator, the source of the electric field eventually when we talk about it. And the other charge is going to be the observer. It's going to be the thing that actually kind of experiences the effect, source of it and an observer. And so I'm going to label things RS and RO a lot in this course. So we're just going to start with that today because it's going to come up over and over and over. Okay. So that's fine. Trying to move the Zoom thing around so I can see everything. Okay. And we won't usually really care about RS and RO separately. What we really care about, the most important vector, is not the separate one, is actually going to be the vector from RS to RO. It points from source to observer. And that's going to be called RSO. So this is from source, that's physically, that's what I'm going to say. But anyways, it's from S to O. We don't know about source and observer yet, but it's from the first label pointing to the second label. Okay. This is a little different, I think, in dynamics. For those of you in that course, it's written as RO O relative to S. I think that's the notation. Did you use that notation in statics? If not, anyways, I think that's the notation that's going to be used in dynamics. These are the same, but in physics, I'm going to write it this way. RSO goes from source to observer. And the way you read this one is the observer relative to S. That's just how I'm going to write it. Okay. Now, could we use our vector addition knowledge to come up with some sort of formula relating RS, RO, and RSO using vector addition? Can I come up with an addition statement that relates all three of these?
Yeah.
What would it be?
RO minus RS equal to that stuff, you know.
Sapon, you're not supposed to jump to the answer. Yeah, you're right. But let me, I want to write it with addition just because I introduced addition above, but you're exactly right, Sapon. All right. So what I would say is, look, tip to tail, RS plus RSO equals RO. Or if you turn it around, you could say RSO equals RO minus RS. Yeah. Okay. So I'm just using vector addition and this triangle to work that out. So RSO, just keep track of the order here. RSO is O minus S. Okay, just keep track of that. The minus signs are going to be crucial, so that's why I'm really harping on this. Okay, so here's what I want you to do, and then we're going to be done. For the picture I've made right here, what is RO? What is RS? What is RSO? What is the magnitude of RSO? And what is RSO hat? We will go through this process over and over and over for problems. So let's start today. Okay. So look at this picture. It's a 2D problem. You don't have to worry about the Z direction. So it's just X and Y. Work it out. And then we'll be, is that right? Yeah, then we'll be done. Whoa, sorry. Okay, who has RO in component form?
Four X plus 5Y.
4x plus 5y, awesome. 4x hat, yeah, that's x
Yeah,
hat,
sorry.
awesome. Okay, what about RS? Somebody else call that one out. I'll have to put you guys on the spot.
Negative 3x hat plus 3y hat.
Good, I agree. How about RSO? Well, okay, you go back up here to the formula. It's RSO is O minus S. So I need to do O minus S, but you just subtract the components. So that's going to give me 4 minus negative 3. It's going to be 7 x hat plus 5 minus 3, 2 y hat. Now, these are nice because they're all lined up with the coordinates. So you can check that if you started here, it would be 1, 2, 3, 4, 5, 6, 7 steps in the x direction, 1, 2 in the y direction. You can see the green arrow has these components. All right. And then how do we find the magnitude of RSO? That's just going to be the Pythagorean theorem. So that's going to be 7 squared plus 2 squared, 49 plus 4 is 53. It's just 7 plus 7.1. I don't have a calculator. Do you guys have a calculator there? Can't be much more than 7.
7.28.
7.28. All right. 7.28. And now, how do I make a unit vector? The way we make a unit vector is we take the original vector and we divide it by the magnitude. So in this case, the original vector, RSO, is 7x hat plus 2y hat. The magnitude is 7.28. So this is going to be 1 over 7.28 times 7x hat plus 2y hat. You can distribute the scalar inside the parentheses if you want, but you can look at the numbers. It's not going to clean up, so there's no point. Just for fun, we could check and see that this thing has length 1. So we could work out the magnitude of RSO hat, and that's going to be 1 over 7.28 squared times 7 squared plus 2 squared, just working out the magnitude of this, squaring the x component, squaring the y component, adding them, take the square root. Well, and you know, where did I get the 7.28 number? It's exactly that. So this cancels this, and it's 1. That's why it's a unit vector. Has length 1. Okay. All right. So that's kind of our lightning review of vector notation. I will just tell you, when we want to work out the formulas for forces from one charge acting on another, we're going to have to go through this process of identifying the source, identifying the observer, coordinatizing the geometry to figure out the force vectors. And we're going to go through this recipe: RS, RO, RSO, RS, magnitude RSO, RSO hat. We're going to have to do this over and over and over. So this is a kind of a good thing to be able to do. So make sure you can do this. Okay. All right. Other questions? No other questions? All right. I will post this file as a PDF. I will upload the video. It's an hour or something. So it'll take a little bit for it to process. So I will upload that and put that on the YouTube video. And I will also link to all the vector calc videos for Physics 1 that I made from last year. So you can see those. Okay, that's all for today. See you guys on Zoom on Thursday. See you.